Hi, I'm Geoff Streeter. I've worked for this company for a little while, if you measure things in geological time. So, as a credit to John Scholes, 1948 to 2019, I thought I would do this in paired back text. John and I first met in 1975 when we both worked for Atkins, and we worked on Dyalog APL together from 1981. I can't claim to have John's presentation ability. That's part of the reason I'm not usually seen on these podia. I think this is only my fourth presentation in 42 years. So some brains react better to visual text, mine included, than verbal text. So you get both. Back in 2013, we had a request from a customer. The customer was suffering from slow startup for his application. The application had several hundred, possibly several thousand functions in his workspace, and his request was for a facility to start with a bare workspace and load functions as their names were referenced. This had echoes of mine and David Crossley's paper in APL 79. Didn't know we were going to get two references to APL 79 in this conference, but there's the second one. But I had the germ of an idea. I raised the idea, which received no enthusiasm and an expressed desire to focus on what was requested. However, I am a natural, non-conformist dissenter. I still thought it was worth pursuing, and we have a policy of a Friday afternoon project for non-management approved experiments. It actually took me a day to produce a first cut, and that first cut, with a demonstratable prototype, made the others realize that this idea might be worth a little bit more effort. So what had I done? Our workspace is divided into pockets. This is our unit of memory allocation. Pocket has a length, a ref count, a descriptor, and some content. The zones are a bunch of fields which say what to expect in the any old stuff. Let's call that AOS for short. The AOS can contain pointers to other pockets. Sorry, Aaron. And the ref count keeps a track of how many pointers point to this pocket. For a lot of pockets, when the ref count reaches 0, the pocket can be discarded and the memory used for another pocket. So for a traditional function, we have several pockets. The stars mark the fields that are pointers to other pockets. The LST, local symbol table, is a pocket of pointers to other pockets. Symbols, the names the function uses, think that's what you get back from quadrafs. Constants, the explicit constants the function uses, things like 1, 2, help. And comments, all the comments in the code these days go into the local symbol table. The fun body is a pocket that does not point elsewhere and defines how the function is split into lines and how it has been tokenized. The next concept you need is of a symbol table. For all versions of Dyalog to date, these are binary trees. So each one has a length, a ref count, something that says it's a symbol, a left pointer to the thing that sorts left, a thing to the sorts right, and a pointer to its value and its name. Each namespace has its own symbol table, including the namespaces like hash and quadric. So that gives you some insight into a workspace. However, Dyalog APL has always supported several workspaces. Originally, this came from how we support paren copy. To do paren copy, we allocate memory for another workspace, load the required workspace into the extra memory, and then copy information from that to the main workspace. In fact, historically, these two workspaces were in different processes because the Dyalog Z8000 we developed this APL on was a 16-bit machine and we only had 64K of data per process. We used pipes to transfer the information. So now we can come to the germ of my idea. If I save the user's workspace in a form where it always loads at a known address, I can set up pointers to the addresses from my main workspace to that workspace. Consider our symbol pocket. It's got a value pointer that can point across that workspace boundary at the header for our function. That's not gained us very much. We still have to read the user's workspace just into a different location. But suppose we map the workspace into that location. For those not familiar with mapped files, a file is mapped into the address space of the process, and portions, pages of that file are only read on reference. So now we can have that user's workspace loaded and nothing has been read. That's fast. Clearly, we do have to do some adjustment to the main workspace, or no code will see the change. But all we have to do is to create the symbols in the main workspace and point them at the appropriate pockets in the mapped workspace. Only when those symbols are used will the map space be referenced. So before, in a normal loaded workspace, we had this sort of pattern where the value points to the header in that workspace. But after, in a workspace with shared code, the value points to into the shared workspace to the actual function header that's there. But bear in mind, in that shared workspace, we still have a value that points there from its symbol. So we come back to my lashed up experiment. Let's put that up a bit. I took a copy of the code that supports zero-quad save. I used some of the code we use for fixing up workspaces as we load them, and used that code to create a workspace at a known fixed address and saved it to file. I could then map that workspace. For this experiment, I actually used defuncts.dwas because it's got a fair bit in it, at that known address. I could walk the symbol table, the main symbol table in hash, and copy the appropriate symbols into the main workspace. Lo and behold, I have a working defuncts.dwas which only gets paged in on demand. This worked excellently on Linux. On Windows, it worked, but not as fast as I'd hoped. The customer is committed to Windows. Poor benighted soul that he is. Why was this? Windows does not page as well as Linux. It also does not create processes as well. The two aspects may be linked as process code is mapped at kernel level in both Linux and Windows. There are things I can do to mitigate that. I have lots of time as we prepare the workspace at save time, so I chose to sort the pockets. The first idea was to sort all the symbol pockets together so that they would be grouped in as few pages as possible. Since I was sorting pockets, I could also sort data pockets by length, so that all those small scalar pockets are packed into only a few pages. The customer, this particular customer, has lots of these. So that was enough to have a working system that met the customer's desire for fast startup on his system. Then we started to realize we had other benefits that were not originally envisaged. So, page that up a little bit. The customer's actual system looks like there's some server for code, and then there's a piece of wet string slow connection, I think it's called Citrix, to a local server room. That's got fast connection because it's on the same machine, and we've now got user processes that are running using that. So we've got user process 0 up to user process n. So now, user process 0 starts up and pages are dragged across the piece of wet string to the local server. These pages are cached there, and when the next user process starts, they're already accessible. So user 1 gets even faster start up than user 0. The cache is maintained by the operating system. I don't have to do anything. So let's revisit the way we allocate memory in the workspaces, note the plural. With our memory mapped approach, we've got a value pointer that points across to the workspace boundary. That pointer from value to the function pocket has caused the ref count to increase. However, this is shared memory, so you may think that all users of that memory would see the same increased value of the ref count. And worse, that we may have a race condition as multiple users decrease that ref count. But as a brilliant part of paging systems, we have something called Copyonwrite. This means that if a mapped page is modified, then it does not change the original, but instead a local page in the user's swap space is allocated instead. So each process that modifies a page gets its own copy. I tried to find the history and inventor of Copyonwrite, but it seems to have had a slow gestation. Hardware support seems to come from the DEC VAX, developed software from BSD 4.4, and today it's pretty universal. For Intel, it goes back to the 386. The driving force for the development was the Unix fork system call that is fundamental to how Unix and Linux create processes. Fork creates a new process identical, nearly, lots of subtleties, to the current process. It is nearly always followed by an exec call to replace the current program with a new, different program. Replicating all of the current process's pages just to dispose of them was too expensive. There are, of course, some specific adjustments needed. That function pocket. The fun body is not a problem. It points to a pocket that does not change and can remain in shared read-only memory. Every user sees the same pocket, apart from its ref count, and that does not change until the function executes. The fun body contains the tokenized code and the definition of the lines in the function. The LST, local symbol table, is more of an issue. It contains pointers to symbols and constants. For this purpose, comments are the same as constants. However, each symbol pocket has a pointer to its namespace. Hash is a namespace, quad-C is a namespace, anything created with quad-S is a namespace, and there are a few others. If your function creates a name, A gets 1, then A is a symbol. But when it's accessed, it belongs to a namespace. Let's come back up a bit. Sorry about this. Okay, so in a shared code file, the symbol points to a namespace in the shared code file. But when the function executes, it needs to access the name in the appropriate namespace in the main workspace. We already have code that copes with this, because it can already happen that code is created in one namespace but executes in another. So we walk the LST and make all of the symbols point to the correct namespace. That's okay, but expensive. It is most likely that the next invocation of the function will be in the same namespace. So we write the new LST pointer back into the function code. This would be okay in our shared code file. Copyonwrite would cope. But in order to avoid doing things to that workspace that would involve accessing all of the pockets, like compaction or garbage collection, we avoid creating pointers in the shared code file space that point back into the main workspace. So it's okay to have a pointer across the boundary from the main workspace to the shared workspace, but I avoid having a pointer from the shared workspace back into the main workspace. So we pay the cost on function invocation of checking if the function pocket is in a shared code file, and if so, create a copy in the main workspace. Then the replacement of the LST is not a problem. Where am I? Back to the original request. The customer wanted to load functions on demand. We have also delivered loading data on demand, another bonus. However, never satisfied, customers never are, the customer wanted namespaces, actually classes, but for me that's the same thing. Not so easy. For instance, similar to symbols, the namespace has a pointer to its parent. That parent is in the shared code file, not the user's workspace. So while we walk the global symbols to put them in the main workspace, we also copy across values that are namespaces. That copy is not complete. Some things in the space can remain shared, functions and data, but not sub-namespaces, although their functions and data can remain shared. We also, at shared code file creation time, can mark symbol values that contain namespaces at a lower level. So the symbol may point to a nested array that contains namespaces. These can also be pulled across as the shared file is attached. Again, we do not have to drag functions and data across. Morton now realised this could give him benefits for isolates. Isolates are separate processes with which APL communicates. They may require a lot of supporting APL code. If each isolate loads a shared code file, then it gets the benefit of not accessing stuff it does not use and not impacting the system memory use for stuff it does not, and not impacting the system memory use for stuff it does not use. I don't think the original customer uses isolates yet. However, really good ideas feed through into strange and unplanned places. I first learned this when IP Sharp introduced packages in the late 1970s. I'm sure the developers did not expect the deluge of applications that completely bent their use. Bob might tell you otherwise.
No, we didn't.
We have seen what you can do. Let's examine what you can't do. At this point, I had wanted to wave around a copy of our book Shared Code Files User Guide, but Lulu, who do our print on demand, will not print less than 50 pages, so I'll have to rely on the screen to show the PDF. And I'll take a sideline. You do know that we do full set of printed manuals if you ask, and we can supply those. And if you don't start ordering them, that facility is going to disappear. So let's bring up this PDF. Okay, in that PDF, there is a summary of limitations. We have some fundamental limitations. Shared code files are read-only. Shared code files have fixed virtual memory addresses. Shared code files cannot be shared across architectures. Shared code files are not workspaces. And this says 64-bit Unicode only. The Unicode, I might question whether that's a fundamental limitation. The 64-bit, definitely. And we have some temporary limitations. All objects saved must be visible from the root of the current workspace. It is not possible to have more than 8 shared code files simultaneously attached. The reason for that is that I allocate each of those 8 slices at 1 terabyte intervals on the address space. We could stretch that, just chose 8 to start with. Cannot paren save or quad save a workspace that has shared code files attached. And attaching a shared code file containing namespaces copies all the namespaces, function and arrays remain in the shared space. We've covered that. And only certain content can be saved in a code file. We can come back here. Okay, so I've listed the current restrictions. Some of those may be temporary. Some are just nudging you in the right direction. No classic. Some are good for good, hard reasons. 64-bit map memory does not go well with a 32-bit address space. We allow the use of 8 shared workspaces, I've mentioned that, concurrently. The 8 slots allocated are at 1 terabyte intervals. I wanted to leave some space for workspaces to grow over the next year or so. No quad WC or .NET objects is likely to be the one restriction you may really notice. Was the customer happy with the solution he had not asked for? Happy enough to be pushing for some further extensions? So I guess the answer is yes. And that's me, done. How did I do for time? Not too bad.